We shall start our discussion of the multivariate normal with a recap of the univariate normal distribution. When we introduced the normal mu sigma square univariate distribution, we did it in two parts. Sigma square strictly positive and sigma square equal to 0. In this case, we had density, and this case was defined separately as a degenerate distribution. Now we shall recast the same definition in a form which will be better suited for generalizing to the multivariate case. In the new formulation, we shall first define only this distribution, normal 0, 1, as the distribution having this as the density. Then, given any mu in R, any real number, and any sigma square greater than or equal to 0, we define the distribution normal mu sigma square as the distribution of y equal to sigma x plus mu. Now, you originally gave me sigma squared, so from this I can make two sigmas, one positive and one negative. It really doesn't matter here whether I take the positive one or the negative one. Say I take the positive one. It will give you the same distribution. So, that is the definition of normal mu sigma squared that I use. Now, if I do that, then the single definition takes care of both the case sigma positive as well as the case sigma equal to 0. And this definition is what we are going to generalize in case of multivariate normal. Now this multivariate normal will be defined for some dimension m. M is some natural number. We take any vector mu in Rm. Earlier we had mu in R. The obvious analog will be a vector mu in Rm. And the analog of this non-negative number sigma square will be an NND matrix which we denote by capital sigma, m by m. In case you do not remember what is meant by NND, it is just something that can be written like a square. So sigma is NND means sigma can be written as A into A transpose for some matrix A. In this case, the sigma was not unique if you allow both positive and negative sign. In this case also, this is not unique. In fact, there are infinitely many choices for this A in general. But I do not care. As long as I can write it in at least one form, I will call it an NND matrix. In the univariate case, we had started with X following normal 0, 1. In the multivariate case, we shall start with x1 to xm, IID, normal 0, 1. Now we are about to define the multivariate normal, which we denote like this. This m, subscript m, denotes the dimension, m-dimensional multivariate normal. This is the mu vector and this is the capital sigma matrix, very much like this notation. Here we defined it as the distribution of y equal to sigma x plus mu. Sigma was any square root of sigma square. So here analogously, this will be the distribution of y equals ax. A plays the role of the square root times x plus the mu vector. The entire thing is a m cross 1 vector. So since it's a random vector, it has a distribution, and it is this distribution which we are giving the name multivariate normal. Now in this case, we saw that sigma could be chosen in two ways, plus or minus. We could, for the sake of definiteness, take the positive sign, but we notice that whether you take positive or negative doesn't matter because x had distribution symmetric around 0. Analogously, we can show that which particular A you take, it really doesn't matter. There are, in this case, infinitely many choices of such A, but whatever A you take, Y may be different, but the distribution of Y will be the same. This fact, that is, as long as A is such that AA transpose is capital sigma, the distribution of Y is the same, which means we do not need to care which particular A we choose. This proof is not very simple and will be taken up in the next video. But for the time being, let's do an exercise to familiarize ourselves with this definition. In this exercise, I just ask you to follow this definition for a particular choice of mu and capital sigma for m equal to 2. So I give you something 10 and 20, and in this case I give you 1, 4. So it's a diagonal matrix. Now you may wonder whether it is a positive definite, whether it's a non-negative definite matrix. The answer is yes. In fact, I will give you one particular choice for A. If you take A equal to 1, 0, 0, 2, just taking the square roots, then you can easily convince yourself that A transpose is this capital sigma. So your job is to start with x1, x2 IID normal 0, 1, then exactly compute what this is. So exactly compute y1 and y2 in terms of x1 and x2 and write down the distribution. In this case, I can tell you that y will have a joint density. And your job is to write down that joint density.